Um, I would like to start with some words about a great anniversary. We have several very important anniversaries this year. First of all, it's 60th anniversary of the Moore Law, with a paper which had been published by Gordon Moore in 1965. And this today's webinar is dedicated to the More Moore Roadmap. But also it's the 100th anniversary of the FET invention, with a Canadian patent which has been published just 1 century ago. So very great year for the for microelectronics and the field effect transistors. Mustafa Badaroglu, as I mentioned, is Director of Engineering at Qualcomm for AI chipset system development, with focus on system technology co-optimization, custom memory for data center, mobile compute, and XR products, and with more than 30 years of industry experience. He holds more than 100 published patents and has co-authored over 100 publications in scientific journal and proceedings. He is also a member of the American Semiconductor Innovation Coalition, the SI2 Alliance, DRAM JEDEC, IEEE IRDS More Moore Chair. Today, his webinar is entitled Drivers and Realms of Distributed AI Computing with More Moore. Please, Mustafa.
Thank you so much, Francis. Thanks a lot for inviting me here. Today I'm going to walk through particularly a few elements coming from from the technology scaling and how it helps for AI era, particularly realization of AI computing, and what device and advanced integration brings to make the scaling sustainable for us. So the title of my talk is Drivers and Realms of Distributed AI Computing with More Moore. Cloud and HAI are integrated elements now of our society. So on the device side, smartphones, automotive, interactive gaming, which is on the other side is the cloud, where the abundant AI computing taking place. And then the edge cloud, which is basically connecting our enterprises, our near computing framework, network of devices, all the way to the cloud, and allowing us a seamless distributed computing across all our ecosystem. So the most important thing is basically how to make this computing distributed, and also for workloads for such as generative AI, make it basically the user experience and also the performance requirements of the computation feasible and accessible to everyone at any place at any time. So on the edge computing, sense and feel is very, very important. Particularly, we need to have native AI interfaces, increase the amount of functionality, basically merging the physical world with compute world, that there is no basic feel of anymore, that you are really learning how to use the computer, but more the other way around. Computer learns what you are doing and then bringing native responses. So integration of all this technology, display, camera, and sensing, all integrated with high performance AI computing, are essential elements for edge computing. Cloud computing is basically storing how we think, basically bringing a more general purpose AI uh, and how to scale up the system with the system interconnect, and then bringing particularly new workloads, basically requiring a lot of memory bounded computation and bringing high bandwidth and high capacity memories close to the compute for abundant computing. So this is basically the connection bond of this is how to bring cloud AI, edge cloud, and edge AI computing all together in distributed computing. So the metrics typically we define for the quality of AI computation is dictated by the technology elements like memory bandwidth, how much memory capacity at per unit volume or unit power, and then number of compute elements, number of max, multiply accumulate units per millimeter square, and also how to pack a high power density system, how to pack increased number of max and increased number of memory bandwidth per unit temperature. So these are key metrics basically to sustain the scalability of AI solutions. So when we look at the system, particularly we need to make the technology available, high volume manufacturability. This is actually the goal of More Moore roadmap, is not only bringing the technology innovation, but also bringing innovation at large scale, manufacturable, and driving the system needs in a sustainable way. So when you look at, especially for AI computing, one observation is that there is now more demand for silicon, thanks to a lot of parallel computing allowed. So performance problem has been basically shifted from having rather than having a one single performance chip, how to create a parallel number of chips, parallel number of cards for deriving the performance. So this is basically meaning that more silicon volume. So this spatial computing is how to make it effective is also enabled by system interconnect, maybe evolving in the near term from chip to chip optical interconnects, and making these systems parallel computation more connected with high bandwidth. So the overall another thing is that the accessibility. So the AI is always on. So its mission profiles are 24/7, and we need to deal with reliability. We need to deal with also the thermal aspects of this continuous operation, the throttling, and how to deliver performance under throttling conditions. The second element is time to market. So these systems are highly requiring high amount of heterogeneous integration, although it's defined as a compute system in the cloud AI, but in edge AI, you need to bring a lot of heterogeneity, not only semiconductor technology, but sensors, as well as the imaging technologies, projector technologies, like you see the snapshot of a XR glass application with a lot of heterogeneous components and technologies enabled in a very, very small form factor, and different integration requirements. So the 3D integration is also getting very, very important for enablement of this small form factor and bundling solutions. Devices are evolving, and heterogeneous integration also evolving at the system level. And then this is basically bringing a lot of new materials next to each other, so which is basically increasing the process complexity. So many of the things are sequentially integrated and with less options to test them. And then this is increasing the process complexity, number of steps and materials, and how to handle yield as well as different integration challenges coming from the process. So the essence of this, this is basically deliver a best-in-class technology and architecture solutions for mobile compute and server products with best use of process and packaging technologies with IP reuse. So here, the evolution of the fabrics, everything is based on reuse. So when you are using one component, you scale the other component, and then at the end, for such complexity is handled in a more modular growth of the individual modules to enable a fast pace of these technologies, which is typically changing sometimes once every 2 years, but these days even once every 6 months. You might want to deliver a product where the technology pace is typically 2 to 3 years new node generation for semiconductor technology. So the sustainability in terms of the time to market and heterogeneity are requiring fast turnaround time to make the devices into the market. I want to talk a little bit about generative AI, why we are considering a lot on memory bandwidth and how to scale up the performance, explaining this simple graph here. So this is a roofline plot. So y-axis is the throughput, token per second. X-axis is the token latency. So basically, if you want to, so x-axis is the arithmetic intensity or batch size. Basically, for every DRAM fetch, you increase the batch size. Basically, you have more inputs for a given DRAM input, and then run parallel users using the same weight coming from the memory. So typically, inference applications requiring a lot of, for a given training set, the data set, you want to generate more tokens, and you want to improve the latency between the token to improve the quality of service, and that requires more memory bandwidth. And this is the region where inference application typically operates. The training part is where you have to operate the tokens with multiple batches and more computation involved. This is more compute bounded for AI compute infrastructure. So typically you come to a limit of compute bound. Whatever you do in the system for the same card or same chipset, you cannot improve the throughput because you need more computational resources. Here, even you have the more computational resources for memory bounded. Only way to improve the performance is increase the memory bandwidth. So this graph is a typical curve that you experience in a AI compute fabric at a trade-off between the throughput and the latency. Typically, the token latency determines is the quality of the service, like how you generate one token after each another. So this is called subsequent token generation. the way to improve the system is to increase the memory bandwidth. And you can see in this graph, whenever we reduce the bandwidth, whatever compute resources you have in the system, you are not able to improve the throughput because of the fact that you are more memory bounded. Your throughput starts to fall off in the graph by taking the latency to for a target latency to the left-hand side. Only way to improve the system is increase the slope of this curve by putting more memory bandwidth to the system, so that for a given latency you might have more throughput by increasing the bandwidth of the system. For a end user point of view, you do a lot of queries, and then we want to have a fast response on the first query. So that's the generation of the first token is highly compute bounded. Only way to improve it is basically bringing more compute resources to the system, where you see every level in this graph is amount of chips that you have to integrate into the system to improve the throughput. But basically for a given latency target, which is basically quality of service, you need to increase the number of cards or number of chips to improve the throughput of the system, or to improve the latency of the system, we need to increase the memory bandwidth. So to realize this, on the device side, we need to bring up energy efficient computation to be able to pack more compute resources into unit volume. And that's enabled by basically transition from one device architecture to another. So the changing a device architecture is not a fast pace, cannot be done in fast pace. Because of the return on investment, also the longevity of the device for multiple performance snubs that can be applied on the same device architecture. So the FinFET device has been successfully delivering the performance for the last decade. And then by the enablement of the driver footprint in the vertical direction, and then with a three-sided channel control, having a better also performance, but at a reduced voltage, enablement of the this better handling of the short channel effects. But even this is not enough, and we need to improve further and make the channel control more efficient by gate-tolerant device, which is the next decade devices, lateral gate-tolerant device, and also improve the driver footprint by stacking more devices on top of each other. So this is basically, now we have started the era of lateral gate-tolerant device to enable this, simultaneously reducing the device area, therefore improvement of the parasitics, and also better channel control for reduced supply voltage. The improvement of different by the enablement of further downscaling of the device that is necessary for continue the More Moore scaling. Now we need to integrate PMOS and the NMOS on top of each other. That's bringing the CFET device, as you can see in this cartoon. And then by disintegration of the functions such as memory and the compute logic, or other type of 3D cube for MAC computation, 3D cube for the memories, basically bringing the 3D VLSI device. These devices are stacked on top of each other, separated by local interconnect or just a few routing layers in between. which is basically fine pitch 3D stacking of these devices. So this can be either done sequentially or wafer stacking, but enabling enormous amount of connection between the device at the resolution of a few tenths of nanometer pitch while putting devices, these different device tiers on top of each other. So if we look at the roadmap, we need to create a device for energy efficient and area efficient computation. That's the device segment of the computation, but also we need to make these devices 2.5D and 3D integration friendly, such that they can be connected in the system, all these different chiplets or different fabrics like power distribution network, system interconnect, protection devices. They can be all integrated in the system fabric. So which is basically system infrastructure fabric also has to scale together with those devices. So this brought a lot of different elements to the technology. For instance, backside functions of the device, which is providing a lot of functions to the other side of the wafer, like backside PDN or clock distribution network or NOC, network on chip fabrics, and then leading into advanced interposer development beyond 2031. In the light of this, for the More Moore roadmap, we are about to release the 2025 edition. You can see different technology inflection points that are occurring in the next 15 years of the device development. So one element is now handover to gate-all-around device starting by 2025, this year, to introduction of the backside functions with that device. And then the second inflection point you see is bringing in by the second half of 2027 high NA EUV and even hyper NA EUV by 2033 forecasted. And then the third element is swaying away from the copper technology to non-copper technology, like ruthenium or tungsten, replacing the local interconnect and even tight pitch metal layers like M1, M2, and M3. And then the CFET device coming in around 2031. And then evolving into 3D VLSI, putting these CFET devices on top of each other on a tiered approach to enablement of different tiers for multiple function segmentation. So, the tier 2 is forecasted by 2031, which is stacking 2 tiers of CFET device. Tier 4, 2037, which is basically stacking 4 tiers of CFET and 6-tier device. And then in regards to all these technology introduction, we have defined detailed ground rules per enablement of this More Moore technology baseline. So such as the interconnect ground rules and introduction of the different device widths, as well as electrical parameters associated that can be enabled with those ground rules that are constituting the interconnect and the device technology. So also some key design rules are also have been shown in the roadmap, such that we can enable the area of the system on chip effectively. For instance, introduction of a gate-all-around device with 3 different device widths. One for the high performance, which is the first row in this rectangle bus. And then high density device for GPU-like fabrics. And then the SRAM device for improved cache density. So these different 3 fabrics requiring a different basically different integration schemes, although they are the same baseline, but the tuning of the device or process centering has to be done considering these 3 bits of the device in the system. One thing that is observed today with perspective of a steep subthreshold device is now reducing, and also increased challenge of variability control. We don't see anymore for the next decade a dramatic reduction of the supply voltage scaling. So effectively, device will go to a continuous improvement of the variability handling. So parallelism by system interconnect is more pronounced now in the technology scaling. So the supply voltage stalled around 0.6 volts starting by 2027. This is the nominal supply voltage. Devices are operated at different supply voltages like 0.5 volt, 0.45 volt, or 1 volt. That's possible. But how to enable these different supplies in a system-on-chip implementation is critical, but nevertheless, the nominal supply voltage of the device has stalled. So to enable the performance scaling, we need to innovate on innovative device contact schemes, continuously improving the source drain contact resistance per unit micrometer. So this is a 2-sided contact value from 260 down to 200, and also improve the spacer or the dielectric K value of the dielectric surrounding the device, particularly the dielectric between the gate and the drain of the device, drain and source of the device, reducing well below 3 down to 2.7 is foreseen in the roadmap forecast. This can be enabled by multiple schemes like integrating air gap next to the device, or different K value, multi-K value device spacer integration together with the air spacer can enable this number. So another element is that we started to communicate in the roadmaps some years ago, bringing in the backside functions to the device. So the backside metallization, as you can see in the cartoon graph that was presented by TSMC last year, IDM. So you have front side of the device, which is used for tight pitch integration only for signaling layers, for routing the blocks and the standard cells connected to each other. And the on the backside of the device is used for backside power delivery. And that's, you see, the device is now totally invisible, and the complete thickness of the silicon is if just 100 to 200 nanometer thickness, allowing the device layer. But you see the access to the device is done from the backside and the front side at the same time. And then to reduce the cost of the integration, so the only a few layers are used to connect it to the device from the backside, a few tight pitch layers, but then immediately evolving into more package-like pitch to be able to connect it to the I/O and the power distribution network on the backside of the die being connected to the laminate substrate. The second inflection point is that was introduced was bringing in the non-copper technology because of copper, the barrier liner scaling is not, as you can see in this cartoon, indication of barrier liner. The amount of volume, metal volume, copper volume you can integrate in the trench is reducing, and also there is also the limit for metallization, void-free metallization to fill the trench with the copper. So that's why for tight pitch layers now there's a transition happening to non-copper. Here is an example for ruthenium, which is also enabling direct etch technology, direct metal etch technology, with allowing to keep the grain sizes larger such that you have better resistivity on those small dimensions, and also eliminating the barrier liner from the sidewall of the metallization trench, ending up with a much larger copper volume on the same CD targeted for the copper. And then the one of the aspects of the technology scaling is how to basically bring in this hybrid metallization layer. For instance, connecting copper with copper via into ruthenium interconnect, or using a ruthenium via which is self-aligned to the ruthenium below, and making the copper more coarse pitch layers using a copper technology. So this example was presented as cross-section shown here last year in IEDM by Intel. And another important element that I just want to highlight is because of the resistance increased by the tight pitch layer, is we need to introduce a high aspect ratio metallization. But this high aspect ratio metallization will create more increased intra-layer capacitance between those two interconnect routing layers. And that's why the air gap also needs to be introduced to reduce the intra-layer capacitance from the interconnect, where you can see the air gap between those trenches. So in the light of this 3D devices and tight pitch local interconnect, by the enablement of this non-copper technology, there is also continuously, this is basically enabling a continuous reduction of the standard cell dimensions, and both on the X direction and in the Y direction. So today, the standard cell baseline is basically bringing bedside metallization, which is shown as the brown layer here, to deliver, for instance, power to the device from the backside. And then introduction of the gate-tolerant devices because of the better driver footprint, allowing a reduction of the Y direction. So this is basically reducing the device height, standard cell device height, enabling below 100 nanometer. And then the generation after 2035, now the PMOS device and the NMOS device can be stacked on top of each other by CFET technology, further reducing the track height of the cell, reducing from 5 track cells to enablement of 3.5 track cells by the CFET technology. So this will allow basically area scaling by without big change on the ground rules of the device. And you can see in this graph this effect where the dimensional ground rule scaling is slowing down mostly because of the electrical limits. Because of scaling further down, you have increased parasitics, you have reduced gate length, reducing the electrostatics of the device. That's basically stalling the gate pitch scaling. And then the interconnect scaling is mostly dictated by exponential increase of the resistance below a certain dimension. So here, for the interconnect, we believe from a forecast point of view, 14 nanometer pitch will be the stalling point for metal pitch scaling. So but even these device dimensions are not scaling well, we still see quite a healthy scaling of the cell height, which is at the end reducing the SOC area for a given function by the enablement of these inflection points. One of the important inflection points that we forecast for 2027 is communicated also by leading IDM and foundries, direct backside contact technology, enabling a less than 100 nanometer cell height, and then the introduction of fork sheet, which is reducing the space to the space between the PMOS and the between the basically devices between NMOS and the PMOS, or between NMOS to NMOS at the cell boundary, enablement of the fork sheet, enabling a standard cell height of 80 nanometer. CFET is further reducing all the way down to below 50 nanometer, enabling now a good device fabric for 3D VLSI. So this enablement of the backside technology and also CFET introduction has also SRAM benefited, bit cell area also benefited from this scaling. And this is basically, these numbers are also well in line with what was communicated by 2 nanometer technology, where we expect to see in by the end of this year, 2025. And you see also a scaling of the bit cell area. But a true transition necessary for the 3D VLSI technology to enable the SRAM capacity, like a 3D SRAM, particularly to sustain the scaling of the devices beyond 2033 for the on-chip memory. So Bringing all these parasitics as well as integration, PPA perspective of the integration, we calculated what can be the GPU matrix that we foresee for AI scaling, all listed, all basically graph in these graphs here. So in the frequency scaling, we see around the era of particle 2D scaling of the device until 2035, 1.5x scaling improvement of the frequency, 3 times reduction of the power, but a continuous increase of the device and 3D scaling, alarming the power density. We forecast around 5x increase of the power density around the 15 years horizon. So this is alarming. So we need to have improve the thermal solutions to continue this fast pace of power density increasing, particularly starting by the 3D VLSI generation. So by the improving the number of max per chip, we expect to see 25x improvement of the TOPS for the integration of multiple max in the device. Then bringing those metrics, one metric is area efficient MAC utilization and energy efficiency of the typical AI processing. So we expect to see a significant compute density improvement, like 400, more than 400 in the next 15 years, while the energy efficiency is improving only around slightly about 2.5x in the next 15 years. Basically, this bringing why we have this gap in the power density and why we need to disintegrate the functions of the compute die or bringing innovative cooling solution to increase the power of the system, tolerable power of the system by innovative thermal solutions, cooling solutions. If you combine those two metrics in one graph, we have a healthy scaling, provided the fact that we can integrate these systems by bringing a package and system interconnect, by bringing a cooling solution. We have 3 orders of magnitude improvement in energy efficient TOPS, improvement with energy efficiency for unit function, the product of those two terms. The reason of these graphs, because of the integration capacity, despite the fact that we have a reduction of the ground rules not happening that fast, the integration capacity still enabled quite good in terms of with regards to more technology capability. So the integration capacity of the MAC computation, which is counted as megagauge per millimeter square. So the 17x scaling across the 15 years. The SRAM capacity increase about 11x in the next 15 years. And then this is bringing basically same as the gates. And here is the absolute numbers that we forecast for a typical inference SoC. 17x, 20x improvement of more Macs across the horizon of the roadmap. So today, actually, the number of Mac units is around uh, around 128K to 132K for a typical AI inference chip. We expect to see in 2039 67 million Mac units in one chip, and then bringing a TOPS of 310,000 TOPS from one chip. Think about today, its standard AI PC can have around 200 TOPS. Now we are talking about 300,000 TOPS by 2039. Provided the fact that we solve all the thermal problems and the system interconnect problems. So this is what is happening in the data center. If you think about a single card with 8 CPU, GPU that are actually integrated in a node, and then we used to see with liquid cooling card systems around 400 watt and 800 watt. Now the tolerable temperature in a single card has increased to 8,000 watts. So now data center is not only called for cooling, but it's also how to create a distributed connection of the cooling solution with a liquid tank here that is distributing the liquid, basically liquid channels across the different nodes of the server farm, but also solutions like highly thermal conductive liquid and immersive cooling techniques to cool down the complete card to continue the scalability of these systems, despite the fact that we have a crisis in the energy efficiency scaling. But this is not environmentally sustainable because you need to now the server plant has to be taught together with a power plant to be able to deliver to the power to this system. But what is happening also an algorithm innovation and system interconnect innovation, improving the amount of AI efficiency with less model sizes, reduce model sizes, different AI algorithms like agentic AI with distributed AI computing, with the vision that I introduced in the first slide. It's a potential for handling the power crisis that is happening in the data centers by making enablement of the distributed AI computation. I want to bring the system interconnect to on-chip interconnect perspective. So the reason of why we have pushed actually the wiring PDR routing problem to the backside, and also to improvement of the 3D architecture much more because of the increased wire length. If you look at today's technology, now the total delay of data path is more than 70% of the single stage delay is contributed to the interconnect related routing. So about 35% of the delay is coming from the local interconnect. This includes also the parasitics of the local interconnect, like capacitance and capacitance formation with the device. And then the backend, particle on the backend, the resistance of the wire. So the transistor part is contributing, for instance, for year 2025 is only around 40%, and we expect to see this number is going to get worse by technology scaling. So there is a work to go introduced by many vendors, bringing basically a single layer or basically ALD based barrier liner technology, introducing composite liner technology, reducing the wire resistance for the copper interconnect, but also bringing non-copper solutions as we expect to see, especially for subtractive metal etch around 2029. And then introduction of via pre-fill technology, improving the barrierless via, that is basically reducing the vertical resistance of the wire. And then the last element that I have introduced was introduction of the backside power delivery is also further improving the performance of the device because of less IR drop due to effective power delivery to the standard cells. So in our roadmap, we have basically introduced the ground rules for the backside interconnect, and also told about what are the functions that can be delivered from the backside by the fast pace of backside processing evolving. So the first generation will be PDN and the IO. Starting by the direct backside contact, we expect to see part of the clock network, clock tree, will be implemented on the backside of the wafer. And then with more enablement of the tight pitch and different device access schemes, it will be possible to implement bus fabric like network on chip at the backside of the wafer to further improve the system interconnect related performance losses while simultaneously improving the area efficiency of the computation. But we need to keep the number of backside layers at moderate level to reduce the cost, because front side and the backside of the number of metal layers will reduce the yield and also will cost the system. That's why the number of backside layer has to be kept moderately low compared to the front side. And this was introduced this year at VLSI by Intel. More details of the backside PDN technology was introduced. So you can see 6 metal layers at the backside of the 2025 equivalent introduction of the technology. So tight pitch layers at the backside, still no direct backside contact in this generation. It's metal contact to the first layer, first level local interconnect, which is M0. So pitch has been relaxed now at the front side, reduced number of front side metals with right balance at the backside, but immediate scaling to tight pitch metal layers to allow better power distribution and better interface to the package at the backside of the wafer. This is basically the skeleton of our roadmap, More Moore roadmap. So it's not only ground rules, but we also detailed talk about all the electrical specs, which are driven from the ground rules. Everything is computation based. What can be achieved from the ground rules, what can be achieved from the electrical specs, all the way to the system KPIs like TOPS per millimeter square and TOPS per watt, which is basically the foundation of the data path, which is determined by the standard cell and the bit cell, electrical figure of merit, and also the integration area density figure of merits, leading to AI figure of merits in the total system. So this is and this can be also this has to be also economically sound. We also cover the defectivity requirement for the roadmap, and you can see as an example for a MPU chip where the die size is changing from 750 all the way to more than the reticle size. We expect to see basically already a stitching generation by 2027, especially by the introduction of the high NA. The reticle size will be now half of today's size, around between 300 and 400. And then that's why stitching is in any case inevitable for MPU chips. And then the number of masks, which is increasing the process complexity with more steps involved per each layer, but keeping the mask count moderately in the same number until the start of the 3D 3D VLSI technologies. So to enable the 3D VLSI, we need to think the compute fabric almost like a memory fabric, introduce extreme amount of redundancy to support the 3D tier, 80% redundancy, repairable. It's not 80% redundancy, but 80% of the die is repairable with a spare count around 5 to 10%. We expect to keep the global D0 level constant across the generation of the technology, but the requirement to improve the D0 per each process complexity has to be improved by 3x across the 15 year of generation. So the spare logic is key actually to enable the sustainable yields to circumvent this increase in process complexity. So together with the yield team, we have been working on what is the tolerable number of defects in wafer for a GPU chip. Typically, you need to deal with these two waveforms. One is the critical area curve, which is the layout features that is actually introduced by the technology scaling and increased pin density, for instance, by scaling of the technology, and then the defect density curve. Combining of these two curves provides the yield curve, which is basically yield density curve, which is the yield curve. Integrating this curve gives the compound yield for a tolerable defect size. And then this brings the number of defects per wafer on the die, where you see on the x-axis the killer defect size for the technology, and then the number of defects tolerable on the wafer to bring an economically sound yield on the wafer. So I will now, just a few slides left for the memory fabric scaling. On the memory fabric in the roadmap, we see a transition from 6F squared to 4F squared by the end of 2027, basically changing from capacitor integrated next to the excess transistor Now the excess transistor will be implemented with a vertical pillar connected to a capacitor pillar. So then after this device generation is used, about this DRAM bit cell generation is used 3 or 4 generations, switching to 3D DRAM might be required beyond 2033, which is basically treating the capacitor like a horizontal pillar, and then treating the DRAM almost like a 3D NAND flash technology, depositing DRAM tiers and then having a single or a few step edge to be able to connect to those devices. Like a vertical bit line and horizontal word line can be one approach. So why this is important? So on the memory bandwidth has to be improved, and you have STCO mitigation to improve it. So one aspect is bringing compute near to the memory, and then second aspect is increasing the memory bandwidth. So this is basically can be improving the I/O speed and also enabling of tight pitch through silicon via technology, I/O tight pitch I/O through the implementation of TSV technology, and to increase with this outside memory capacity, we also need to simultaneously improve the cache size inside the chip by introduction of 3D cache and or 3D stack memory like it is introduced in the HBM technology. But these chiplets also more compute and more memory bandwidth. Also, I/O bandwidth has to be concurrently improved by bringing network on chip or network of chiplets to interconnect those chiplets on the overall system. So the takeaways from our presentation is Edge Cloud AI and enriched machine interface driving the silicon volume, therefore driving the More Moore roadmap. IRDS roadmap, we try to connect the HBM capability to AI figure of merits to enable the scaling. Gate-all-around and the backside metal and the 3D memory augmented by system interconnect are the main technology drivers enabling the scalability of the AI. And in the 2025 edition, we updated our SRAM roadmap. We changed our driver from AI from mobile processor to NPU inference chip as the main use case driver. And also we introduce a deep dive to how to bridge the memory wall and the compute energy reduction in our roadmap by listing some key system fabrics to enable the scalability of high performance AI systems. So that completes my talk. Thank you so much for your presence and listening to my talk.
Thank you very much for this great presentation, for this updated More Moore roadmap. So if you have any question, you can use the chat.